All right, good morning, ladies and gentlemen. We'd like to say welcome to this session. We are going to have a very beautiful talk by Professor Yaowu Zhang. He is from Shanghai Institute of Mathematics and Interdisciplinary Sciences. He also affiliated to Shanghai University of Finance and Economics. He is going to talk on adaptive independency test through the generalized HSIC, where he can later define very well. Please join me in warmly welcoming Professor Zhang, please.
Okay. Thanks very much for the introduction. And it is my great honor to be here to share my recent work on independence testing. So, measuring and test nonlinear dependence and testing for the independence between random vectors is an important and fundamental problem in statistics. It has a wide range of applications in many related fields, such as it can be applied to model checking, variable selection, and graphical modeling and causal inference. There are also various variants of independence, such as the mutually independence, conditional independence, and two-sample problems. And they also have many applications in various subjects. So when we consider the measuring the dependence between two univariate random variables, there are several classical measures in textbooks, such as Pearson correlation, the Condorcet tau, and the Spearman's rule. As we know, the Pearson correlation can only detect the linear dependence, and the Condorcet tau and Spearman's rule can only capture the monotonic nonlinear dependence. So although these measures are widely used in the literature, they may fail to detect some certain kind of complex associations. So to address this issue, there are several rank-based measures proposed in the literature to measure these kind of so-called arbitrary nonlinear dependence. Still, when the variables are univariate, we can use the Hoifding and the BKR measure. These two measures are developed through integrating the square difference between joint and marginal cumulative distributed functions. So recently, the Chatterjee's rank correlation has gained many attentions. This measure is quite simple. It is important to note that the Chatterjee's rank correlation and the CCD is short for the composite coefficient of determination and the sliced independent test. All these measures have the same expression at the population level. So the difference lies in that they use different ways to estimate the index. So the Chatterjee's rank correlation, it uses the one nearest neighbor to estimate. The composite coefficient of the determination, this method uses kernel smoothing, and the sliced independence testing, it uses a slicing technique to estimate the conditional expectation. So although all these measures can measure the arbitrary nonlinear dependence, they are designed for univariate random variables because they are all rank-based. So as we know, the multivariate random variables, there is no good way to define their rank. So it is difficult to generalize these measures to multivariate cases. So if we want to deal with multivariate random vectors, there are the distance and the kernel-based measures can be used to assess the nonlinear dependence between random vectors, especially when the dimension is arbitrary. So we can note that there are two popular measures, such as the distance correlation and the HSIC. We can note that both the distance correlation and the HSIC are developed in the same year, 2007. But they are popular in different communities. The distance correlation is popular in the community of statistics, and the HSIC is popular in the community of the machine learning. So while they are popular in different communities, they have some connections. For example, it is shown that both the distance correlation and the projection correlation used in the statistics community are the special cases of the HSIC in the popular in the machine learning community for distinct metric spaces. So we can see that all these measures share some similarities, and it can be seen that the HSIC is a more general measure because it contains the distance correlation and the projection correlation as special case. So although these measures are shown to be capable of capturing nonlinear dependencies for arbitrary dimensions, their theoretical developments are derived under the fixed dimension paradigm. That is to say, they can detect the nonlinear dependence for arbitrarily fixed dimensions. So nowadays, we may face the high-dimensional data. The high-dimensional data present new challenges for the distance and the kernel-based measures. For example, Professor Ramdas observed that the power of both the distance correlation and the HSIC may diminish rapidly as the dimensions increase. So their result is based on simulation findings, numeric findings. And later, Professor Zhu demonstrates theoretically that the distance correlation and HSIC can only detect linear dependence if both P and Q greatly exceed n. Here, P and Q are the covariant dimensions, and n is the sample size. So, this is a theoretical result. So we can know that if the dimension is very, very high, we can the distance correlation, both the distance correlation and the HSIC will degenerate to capture only linear dependencies, although they are designed for capturing arbitrary nonlinear dependencies. And last year, it is revealed that the HSIC is unable to measure specific higher orders of polynomial dependencies, even when the dimension is only moderately high. So this result generalized the result in 2020. So this result shows that when the dimension is fixed, we can capture arbitrary nonlinear dependence. When the dimension is very, very high, we can capture only linear dependence. So if the dimension is between fixed and very, very high, how the ability of the HSIC degenerates from measuring arbitrary nonlinear dependence to only measuring linear dependence. The degenerate is a certain kind of polynomial orders. So given these limitations of the both distance correlation and the HSIC, in this work we have three goals. The first one is we want to provide a way to understand why and or understand the properties and limitations for HSIC in high dimensions. That is to say, we want to know why the HSIC will degenerate from measuring arbitrary dependence to only linear dependence in high dimensions. This to provide some kind of insight. The second one is that we want to develop, given that such limitations, we want to develop a new measure that has the potential to detect the nonlinear dependence in high dimension. Because we have shown that we have known that the HSIC will only detect linear dependence in high dimension. So we want to develop a new measure to overcome this issue. So the last one is that given the newly developed the measure, we want to conduct data adaptive test based on this new measure. We expect that the new data adaptive test will exhibit greater power than the traditional HSIC-based test in high dimensions, especially when there is a nonlinear dependence between the random vectors. And even in the presence of linear dependence. So we expect that the new test, even there is only linear dependence, the new test will achieve a greater power than the HSIC. So to achieve these three goals, we first briefly review the distance correlation and the HSIC. The distance correlation is defined as the weighted L2 norm of the difference between the joint and marginal characteristic functions. So this is the original definition of the distance correlation. The problem is that how to evaluate these integrations. In general, this is not straightforward. So they show that with some properly chosen weight functions, if we choose the weight functions as some special choices, this integral has a closed form. We can see that the final expression consists only some certain kinds of distance and expectations. So at the sample level, this expression can be estimated easily. And the HSIC, this is the definition of HSIC. We can see that this form is quite similar to the distance correlation in terms of expression. And here the K and L are two kernel functions. That is the HSIC, the performance of HSIC relies on the choice of the kernel functions. In general, we focus on the translation invariant kernels that can be written in this form. We consider such choice of kernels because the commonly used kernels are in this form, such as the Gaussian kernel and the Laplacian kernel. So our first finding is that the HSIC can also be written if we use the translation invariant kernels. The HSIC can also be written as a weighted L2 norm between the difference between the joint and the marginal characteristic functions. And the weight functions satisfy that they are positive, absolutely integrable, and symmetrical above zero, and attain its maximum at zero. So the first claim, such as it can be written in this form, and the weight functions are positive and absolutely integrable, these are direct consequences of the Bochner theorem. So this has already been established in the literature. And it is the more fundamental result lies on the last assertion. So we will show that the property of symmetric above zero and attain the maximum at zero provide certain kind of insight to understand why HSIC can only detect linear dependence, and it also motivates us to develop the new measure. Here we know that the weight functions are positive and absolutely integrable. We know that these two properties indicate that the two weight functions are proportional to a certain kind of probability density functions, because the probability density functions are positive and absolute integral, and the integration equals to 1. So this result can establish the how we choose the weight functions to that result in the commonly used HSIC. For example, if the weight functions are chosen to be normal, it leads to the Gaussian kernel HSIC. If we choose the weight functions to be multivariate Cauchy, it leads to the Laplacian kernel HSIC. And these two results are direct implications from that the weight functions are probability density functions proportional to that. And more importantly, when we know that when Laplacian kernel is used with the extremely large bandwidth parameters, we can show that the HSIC is asymptotically equivalent to the distance correlation. And this also establishes the connection between the distance correlation and the HSIC. That is, the distance correlation is essentially the equivalent to the HSIC by choosing the Laplacian kernel with the extremely large bandwidth parameters. And more importantly, as we said that the key observation from our first finding is that the weight function is symmetric and has a peak at 0. Because the HSIC is the integration between of the weighted difference between the joint and marginal characteristic functions, and the weight has a peak at 0. So we know that although it can aggregate all the difference between the difference, it puts more weights around there. So it may be more sensitive to the difference between the weight functions, the difference around there. So we want to know how the difference is if the weight if the T and S are around 0. To this end, we can utilize the Taylor's expansion, and if both T and S tend to 0, we can show that this straightforward expression. The difference between the joint and the marginal characteristic functions and the leading term is the covariance between T transpose X and S transpose Y. So we can see that this is obviously the linear dependence between X and Y. So we know that although the HSIC or distance correlation can capture arbitrary dependence, it puts more weights around 0. And around 0, it mainly captures the linear dependence between X and Y. So this suggests that partly explains why the HSIC can only detect linear dependence in high dimension, because it may be more sensitive to linear dependence. And we can also conduct a toy example to illustrate this phenomenon. We let Y and X in this equation. And we know that in this there is no error term in this model, and we use C to control if C equals 0 and Y depends X linearly, perfectly linearly. If C equals 1, Y depends on X purely nonlinearly. So the parameter C controls whether Y depends on X more on the nonlinear side or more on the linear side. And from this figure, we can clearly see that if C is around 0 or if C is small, the power is very high. And C is around 1 or is large, that is Y depends on X more on nonlinearly, the power drops significantly. So this toy example further confirms our finding that the HSIC is more sensitive on linear dependence rather than nonlinear dependence, although it can theoretically capture arbitrary nonlinear dependence. We know that this example is built on a univariate case, and here x is a univariate and y is also univariate. So if we want, our focus is on high-dimensional case. So we can show that we can also show that if the dimension is very high, with Taylor's expansion we can derive that the HSIC will tend to 0, and the leading term is expressed as this. Essentially, this term characterizes the weighted sum of linear dependence. So this is consistent with the earlier finding by Zhang 2020. And the HSIC will tend to 0 and can only capture linear dependence. So from this point of view, we can know that the y HSIC will degenerate to capture linear dependence. This is mainly because the HSIC in high dimensions, the HSIC will degenerate. It degenerates to 0, with the leading term being the linear dependencies. So how to overcome this issue? The idea is quite straightforward. And as we know, why it degenerates to linear dependence? This is because the weight function peaks at 0. So the HSIC has, as we have demonstrated, that the HSIC will bias to linear alternatives because the centered and peaked nature of the density function. That is the weight function has a peak at 0. So how to enhance the sensitivity of the HSIC to nonlinear dependence? This is quite easy. If we shift the weight function to another point, that it is now not centered at 0, but it peaks at another point. So the resulting HSIC will may be more sensitive to other kind of nonlinear dependencies. Okay, that is if we can modify the original expression of HSIC as in this form. We incorporate the mu1 and mu2 as two shift parameters. So here the incorporation of mu1 and mu2 allows us to potentially emphasize the nonlinear dependence between x transpose mu1 and y transpose mu2, and we can see this later. So now the question is. Now the question is how to evaluate the integration. Does it still have a closed form expression? Because we have demonstrated that the weight functions are proportional to some certain kind of probability density functions. We can easily derive that it still has a closed form expression, although it seems somehow complicated. But we can show that this can also be estimated within a big O n square times p plus q steps. So we can this final expression can also consist some kernels and cosine functions and expectations. So this can also estimated easily, and we can also similar to the distance correlation and the HSIC to standardize this to range from 0 to 1. And we can show that this kind of generalized the HSIC is non-negative and equals 0 if and only if x and y are independent. And more importantly, if we choose mu1 and mu2 to be both 0, the generalized HSIC reduces to the classical HSIC. That is why we call this the generalized HSIC. So now the question is whether the newly developed the generalized HSIC can capture a nonlinear dependence in high dimension. So similar to the traditional HSIC, we use the Taylor expansion to investigate this. We can show that the generalized HSIC has a leading term of this, and more importantly, this will not degenerate to 0. So as we have demonstrated earlier, the HSIC will degenerate to 0 in high dimension, and the leading term is the covariance between X transpose S, T and Y transpose S. That is the linear dependence. And here, the generalized HSIC will not generate to 0. Firstly, it will converge to a constant. And secondly, and more importantly, the leading term, the constant is that contains the nonlinear dependence between x and y, because this consists of certain kinds of cosine or sine in this. This is certainly a nonlinear transformation of x and y. So if we choose the location parameter mu1 and mu2 properly, the generalized HSIC will be sensitive to certain kind of nonlinear dependence in high dimensions. But we know that it relies on the choice of mu1 and mu2, and we will derive a data adaptive way to select this. Now, the generalized HSIC can we can estimate this in this form, the U statistic. And we can show that this, although this, it seems that it will require a big O n, very complicated. So we can show that it can be calculated within a big O n square times p plus q steps. And we can show that this kind of estimation, the generalized HSIC at the population level is inconsistent under the null and root inconsistent under the alternative. This is a standard result for the generalized HSIC, and is similar to the distance correlation and the HSIC. So this result indicates that the generalized HSIC, when the dimensions are fixed, the generalized HSIC can be used for independence testing with arbitrarily pre-specified the mu1 and mu2. So the choice of mu1 and mu2 may not be sensitive if the dimensions are fixed. But as we have demonstrated earlier, as the dimensions increase, the choice of mu1 and mu2 may play an important role because it has an impact on the leading term. So in high dimensions, selecting mu1 and mu2 are crucial for the final power of the resulting test. For example, if we set mu1 and mu2 are both 0, the generalized HSIC will reduce to the traditional HSIC. And we know that the traditional HSIC will only detect linear dependencies in high dimensions. So if there is nonlinear dependence, there will be no power. So consequently, if the selecting mu1 and mu2 adaptively is crucial in high dimensional scenarios. So to select the parameters mu1 and mu2, intuitively we can find some kind of mu1 and mu2 that maximize or empirically maximize the generalized HSIC at the sample level. So, but we can see that this kind of directly estimation of mu1 and mu2, and then apply the estimated mu1 and mu2 to perform the independence test will suffer from at least two challenges. The first one is a computational issue. As we know, the generalized HSIC will require a big O n squared times p plus q steps. So when optimizing the mu1 and mu2, the algorithm will require to compute the generalized HSIC at the sample level and its gradient in each step, in each iteration. This procedure will involve this big O n squared times p plus q steps per iteration. This is quite computationally expensive, especially when the sample size is large or the dimension is high. However, we know that by proposition 2 that the dominant term of generalized HSIC is this kind of covariance between some transformed version of x and y, and the covariance can be calculated very easily. So this suggests that we can optimize the leading term instead of the entire generalized HSIC in high dimensions. So this approach will reduce the computational cost to big O n times p plus q steps per iteration. So this will greatly reduce the computational cost. So the other challenge is that the identifiability issue. So we know that the generalized HSIC equals to 0 for arbitrarily chosen mu1 and mu2. So if we, under the null hypothesis, if we optimize the sample level generalized HSIC, and the estimation will not converge to any stationary points, because any choice of mu1 and mu2 will converge to 0. So if we perform the test based on the optimized parameters, it may inflate the type 1 error rate. There is some easy way to address this, because, for example, we can split the data. We split the data into two halves. We use the first half data to optimize for optimization to find some mu1 and mu2. And we use the second half data to perform the test. This procedure can indeed address the issue of the inflated type 1 error. But because we only use the half of the data for testing, then the power will there may be some certain kind of power loss because we only use half of the data for testing. So to overcome this issue, we suggest to add a penalty term to in the optimization problem, and the incorporation of the penalty term enforces that under the null hypothesis, the estimated mu1 and mu2 will converge to a stationary point at 0 if we, for example, if the penalty we use the L1 norm penalty. Intuitively, under the null hypothesis, the covariance is very small because for arbitrary mu1 and mu2, this covariance will converge to 0. And in this case, the penalty will dominate the covariance at the first term covariance. So maximizing these summations is some kind of approximately equivalent to maximizing the minus penalties. And if we use, for example, L1 norm penalty and minimizing the L1 norm penalty is certainly there. So this can address the issue of the unidentifiability issue. And more importantly, when under the the alternative hypothesis, and the estimated mu1 and mu2 hat are expected to be close to the some mu1 star and mu2 star. The mu1 star and mu2 star will maximize the leading term of the generalized HSIC, or approximately maximize the generalized HSIC. So the final test statistic will converge to 0 in probability and converge to some kind of a large number on the alternative hypothesis. And consequently, this kind of test would be powerful in practice. So this is the result, the theoretical result for the our adaptive test in high dimensions. First, we show that under the null hypothesis, the scaled version of the test statistic will converge in distribution to a standard normal distribution. So, more importantly, we by comparing the existing literature for the HSIC, we can know that our statistic has the same asymptotic distribution with the traditional HSIC under the null hypothesis. So we can know that the critical value for the generalized for our adaptive test procedure is the same as the traditional HSIC based test. So this is the result on the null hypothesis. And under the alternative hypothesis, if on some certain kind of condition for the signal, we have the scaled version of the test statistic will converge in probability to infinity. Compared with the null hypothesis, we know that if this condition is satisfied, our adaptive test will have power approaching 1. So this ensures that our test can be powerful in high dimensions, even when the nonlinear dependence exists. This is because this condition, the T can characterize nonlinear dependence in high dimensions. And more importantly, the last assertion is that if this kind of inequality holds true, we have that our data adaptive test statistic is larger than the traditional HSIC under the alternative hypothesis. So recall that we have discussed that under the null hypothesis, our test statistic has the same asymptotic distribution as the traditional HSIC. And under the alternative hypothesis, our statistic is larger than the traditional HSIC. This implies that our test is more powerful than the traditional HSIC, as long as this kind of inequality holds. So for this result, we have discussed the 3 implications. The first one is that our test statistic is asymptotically equivalent to the traditional HSIC. And the second is that our test can have power approaching 1. And the last one is that our test is more powerful than the traditional HSIC. So we see that this inequality, if this inequality holds, then we have that the final assertion that our test is more powerful than the traditional HSIC. So we investigate is this assumption of inequality mild in practice. So we find that it is really reasonable to assume this kind of inequality in practice, because as we have shown in our proposition 1, the traditional HSIC is of small o1, and the generalized HSIC, because of the optimization, we know that the generalized HSIC is approximately this one. And this one will, in general, be bigger one. So this is greatly larger than the traditional HSIC, and hence this kind of inequality will hold true easily. Let's take a simple example to see this. We consider x to be a standard normal, and y depends on x linearly. And if we use the Gaussian kernel, and we can easily verify that the traditional HSIC is of a small O1. And the generalized HSIC is larger than this quantity and is clearly a bigger one. So this kind of inequality will hold trivially. So we can see that in this case, y depends on x linearly. That is why the HSIC will have power, and our test will be more powerful than the HSIC, because our test is larger. Our test statistic is larger than the HSIC, and they both have the same critical values. So next we perform several numerical studies. We first show that our test will can maintain the type 1 error rate. So we generate the p-dimensional x and q-dimensional y independently from the joint normal distribution. And according to this table, we can see that this is our proposed data adaptive test. And the G represents the Gaussian kernel, and L represents the Laplacian kernel. And the HSIC represents the traditional HSIC. And the DC represents the distance correlation. And the MDCOR represents the marginally aggregated the distance correlation proposed by Professor Zhu 2020. And the last one represents the projection correlation and together combined with variable selection. So we can see that all these methods can control the empirical type 1 error rates. So and this indicates our and more importantly, we can see that our generalized HSIC and traditional HSIC have almost the same the type 1 error rate. This confirms that we have shown that the asymptotic distribution of the generalized HSIC adaptive test and the traditional HSIC are exactly the same. And we also consider these 4 examples models to investigate the power performance. And in model 1, y depends on x linearly. And in model 2, this is a heterogeneous model. And in model 3, y depends on x nonlinearly. There is a quadratic form. And in model 4, there is a theoretical relationship between y and x because we use the cosine function. So we show a part of the final simulation results. We can see that when in the first model, that is y depends on x only linearly, almost all methods can maintain the empirical power at a high level, even when the dimension is high at both p and q are 500. However, when there is only a nonlinear dependence in the model, such as models 2, 3, and 4, only our method can maintain the empirical power at a very, very high level, and all other methods has a degenerate. The power drops significantly. So we also examine the performance of our method when the signal is relatively sparse. So, and we also consider the aforementioned 4 models, and we let only the first 5 entries of y is dependent on x in all the 4 models. And we can see that when the dependency is relatively sparse, and the power of our method degrades compared with the dense cases. However, the power of our method is consistently larger than the competitors. So even in the sparse setting, our method is also very, very powerful. We can see even in this linear model, the projective model, and the heterogeneous model, and the quadratic and the cosine model. So So in conclusion, in this work, we have addressed 3 issues. The first one is that we conduct a comprehensive examination of the traditional HSIC, and from this this kind of investigation, we can understand the properties and limitations for the HSIC in high dimensional scenarios more clearly. It helps us to understand why the HSIC can only capture linear dependence in high dimensions, because this is mainly because the weight functions is symmetric about 0 and peaks at 0, and around 0 the difference between the joint and marginal characteristic functions are essentially the linear dependence between x and y. And secondly, we propose the generalized HSIC to enhance the sensitivity of traditional HSIC to nonlinear dependencies. The general idea is that we can shift the peak location to vary the dependence from linear dependence to certain kind of nonlinear dependence. And lastly, we develop a data adaptive test based on the generalized HSIC. And this kind of data adaptive procedure ensures that our generalized HSIC can outperform the traditional HSIC based test, even when there is only linear dependence. So this is all for my talk. Thanks.
Wow, thank you so much, Professor Zhang. Any question for Professor, please? Any question? Question, please. Okay, maybe I can be an icebreaker. On one of the rank-based measures that you have shown us, you told us that these rank-based measures are designed for univariate, and it might be very difficult for multivariate. So, how did you just fill the gap of the difficulty that you face for the multivariate part, as we are interested in that, for example?
Okay, so as I thank you for this question, and so these measures are developed through the ranks. So we can say such as 1 is smaller than 2, we can, if the one opposition is 2 and the other opposition is 1, so the we can easily put the opposition of 2 ahead of 1. Yeah. So if for multivariate cases, for example, x1 two-dimensional, the first in the first dimension, the first observation is larger than the second, and in the second dimension, the first observation is smaller than the second. So we can not rank the two observations. So this is why they may be difficult to be generalized to the multivariate case. And in practice, in many cases, we may be interested in the multivariate cases. For example, we want to understand how such as the salary is related to such as education and I don't know, the height, whatever, and there may be many features. So it is important to generalize to develop the measures that can be used for multivariate random variables or even arbitrary high dimensions. Yeah.
Thank you. Maybe second question. Other thing is on theorem 1. On theorem 1, you found some very interesting result that the peak value is at 0. So how did you verify that?
So you mean this?
Yeah, sure.
So what?
Yeah, the peak is at 0, right?
Yeah.
So how did you show that?
I show that in this theorem. Yeah. Sorry. In this theorem, yeah, the HSIC can be expressed in this form, and the weight functions attain their maximum when T and S are both there. So this means that it peaks at there. So we next investigate how the performance is around there. Yeah.
Okay, that's great. Thank you. And one last question that I have for you is the penalty theorem, which is also another very interesting thing that you have showed us. So how did you choose the penalty term?
Oh, sorry, I didn't mention the detail. Yeah, in practice, theoretically, the penalty should satisfy certain kind of assumptions or conditions. Yeah. In practice, I simply used the L1 norm penalty. Yeah.
Yeah, great. Thank you.
Okay. Thank you.
Okay, from the audience once again. Question, please. Okay, great.
You said that you add parameters mu1 and mu2 to deal with the nonlinear dependency through the exponential function.
Yeah.
Can this deal with other kind of nonlinear dependencies?
Oh, sorry. Yeah, this one. Yeah. This expander, there is an imaginary component in this. So this is essentially cosine and sine. Yeah. So we know that every function can be approximated by the combinations of cosine and sine. Yeah. So so somehow this is a basis of arbitrary function and the strongest basis. Yeah. So maybe we can find some other forms in this form, but this form is originated from the HSI, the formula of traditional HSIC. So finally, the leading term is in this form. Yeah. Okay. Thank you.
What else? Any other question? Okay, if there is no question, let's once again thank Professor Zhang from Shanghai.